as the title says, this is about Java and the Raspberry Pi. Now, I'm glad to see the room is very full. So, show of hands, who's got a Raspberry Pi? Okay, I know that there's probably a lot of people here who do have a Raspberry Pi. Who had a Raspberry Pi before yesterday? Fewer people, but no, I think this was really good because we gave out a lot of Raspberry Pis as part of this part of the conference. So what I'm going to do today is I'm going to talk to you about the ideas behind what you can do with Java on the Raspberry Pi. Because clearly there's some very, hopefully, very interesting things that you can do with this. And I've got to say that I've got a bunch of demos here, and the demo gods do not always shine, or do not always look on me very kindly. So we'll see how well things work when we actually get to that point of the presentation. So moving right along, I have to put this slide up because this is, clearly an Oracle presentation, so we must make sure that you're fully in compliance with our safe harbor statement. So you've had enough time to read that, so we'll move on. Now, in terms of what I'm going to talk about today, I want to talk about the Raspberry Pi itself and where it came from, a little bit about the details about it, because it is this really kind of cool thing. So I want to make sure that you understand exactly what you've got in terms of the Raspberry Pi. I'm going to talk a bit about ARM processors as well, because that's really the heart of the Raspberry Pi, and it's worth spending a few minutes just understanding, how ARM processors came about, because personally I find that very interesting. Hopefully the historical perspective on that will also be interesting to you. Then we'll get into the real sort of meat of the presentation, and we'll talk about what we've done in terms of putting Java, the runtime, on top of the Raspberry Pi, and also then what you can actually do with Java in terms of the demos and so on. And then at the end I'll show you the demos. So let's start with the Raspberry Pi then. Now I put two pictures up here because these show the two revisions of the Raspberry Pi board. The one on the left is the one that came out first, and that was the very first build. That only had 256 megabytes memory. The one on the right is the slightly newer version, which is the one that everybody who was given a Raspberry Pi yesterday got. So that actually has twice as much memory. It's got 512 megabytes of memory. There's a couple of other minor differences on there, which I'll kind of highlight as we go through, but nothing radically different. Essentially, it's the same thing at the bottom. So let's talk about the Raspberry Pi. Now, the Raspberry Pi came out of a project that was started back in 2006. And the project started out in the UK because what was happening in the UK, and I'm actually seeing this myself because I have a son who's 6 years old. My son is now starting to do ICT, as we call it at school, and that's Information and Computer Technology. It's where they start teaching children about computers. And one of the problems that people at university saw with the children coming out of school into university was they really knew nothing about computer science. What they were being taught in ICT was more about how to use Word, how to use Excel to create spreadsheets, how to write a web page using HTML. They weren't learning about computers in the sense of programming them, understanding what the fundamentals were, and so on. And this project was really about how to change education for school children, primarily in the UK, but then obviously around the rest of the world as well. And it was inspired by something which happened way back in the 1980s. And I remember this because I was actually at school at this time. And there was this thing called the BBC Micro, which was a computer that was created on behalf of the BBC in the UK in order to have education for the population about computers. Now, you've got to remember that this was 1981, so this is way before the internet. This was really just about real computing again. And they had this program called Micro Live. Now, the Raspberry Pi, as I said, was really inspired by that in terms of getting children interested in the idea of computing again. So they launched this on February the 29th last year, and the first production run was for about 10,000 boards that they had built. There were two big suppliers that were delivering them in the UK. There was one that's called RS, which is used to be called Radio Spares, and then the other one is Farnell or Element 14. And both of them had their servers brought to their knees on that day because so many people were trying to order the Raspberry Pi. Now, you've got to understand that RS and Farnell are two of the biggest electronic component suppliers in the UK. They supply an enormous number of things. So their systems are set up to deal with a lot of hits. But both of their servers got brought to their knees on that day. And RS figured that they had over 100,000 pre-orders just in one day for these things. Currently, production runs running about 4,000 boards a day. They've moved the production from China, which is where it was done originally, back to the UK. So there's a Sony factory in South Wales that's now churning out these boards. And the current estimate is that in the last almost year, they've sold about 1 million of these Raspberry Pi boards. From a technical point of view, the specification that you get of the Raspberry Pi is that it's a single chip package that you can have in the center of the thing. So if you look at it, you've got a little black square in the middle of it, and that's really the heart of the machine. What's in there is an ARM processor, and so it's got an ARM 11 core that runs at 700 megahertz by default. The package itself was produced by Broadcom. That's primarily because Eben Upton, who's one of the founders of the Raspberry Pi Foundation, also happens to work for Broadcom. One of the nice things that they've done more recently is when you download the distribution of Linux from the Raspberry Pi website and you first boot up your Raspberry Pi, you get a sort of set of menu options that you can select various things from. And one of those is you can set to overclock the processor. So even though it runs at 700 megahertz by default, you can actually clock it up to 1 gigahertz without invalidating the warranty. If you want to try really hard, you can actually run it at over a gigahertz. There are people who've clocked it to about 1.2, 1.3 gigahertz. And, stability might be an issue. Lifetime of the device might be an issue as well. But certainly up to 1 gigahertz seems to work very nicely. I clock mine at 900 megahertz simply because that seems to be a reasonable speed, and I've had no problems at all with stability or anything like that. Memory, as I said, was originally 256 megabytes. Now it's 512 megabytes. That really did make a difference in terms of performance, moving from the earlier revision of the board to the later one. Having twice as much memory, as I'm sure you'd expect, makes things run faster because you can actually store more things in memory. One of the limitations on memory, unfortunately in this, is the bandwidth that you get between the processor and the memory. So that's something that we obviously can't work around, but it's just a fact of the cheapness of the components that they're using. So, yes, you could have a faster bus, but it would make it more expensive. In terms of the input and output that you get with this is, again, sort of incredible what you get for $35. On there's two of these boards that they now produce. There's a Model A and a Model B, and both of those were actually named after the BBC Micro. But just out of interest, anybody here have a BBC Micro? Good, at least one person did. Okay, so what you get is video out. So you've got HDMI and you've got composite video. The reason for that is that in order to make it cheap and make it easily accessible for schools and so on, rather than having to have a specific monitor, they also wanted it to be able to plug into a television, so you didn't have to buy a monitor for it. There's an audio out plug, or socket I should say, which will give you audio. There isn't audio in, so that again is a slight limitation. So there's no microphone input, only audio output. But you can use one of the USB ports and you can connect a USB microphone to that if you want to. Speaking of which, there are 2 USB ports available. This is only on the Model B. The Model A is cheaper and it doesn't come with the USB ports. I think it comes with 1 USB port rather than 2 USB ports. And the Model B has an Ethernet port as well. Other nice thing, which allows you to do more exciting things, is the fact that you've got a bunch of pins that are soldered onto the board. And those give you access to various internal parts of the system through what are called GPIO, general purpose I/O. There's connections to a UART for universal asynchronous receive and transmit, or serial communications. And then there's also SPI and I2C interfaces supported as well. So you can connect a variety of different things to the Raspberry Pi fairly easily. So let's talk about the ARM architecture, because this is worth spending a little bit more time talking about, because this is obviously what we're using in the Raspberry Pi. And this is a bit different to what we use in our laptops or desktop machines. Now, me being old, I like to look at history because I've lived through some of this. So I've put in this little brief but interesting, or hopefully interesting, history lesson about this. So ARM, which is hugely popular at the moment and hugely successful, came about because way back in the early 1980s, there was the BBC Micro project. And this came from a company based in Cambridge, UK, not Cambridge, Massachusetts, Cambridge, UK, which was called Acorn. And they developed the hardware, they built the hardware and sold it on behalf of the BBC. What they then wanted to do after the BBC Micro was so successful was to go the next step and actually start making commercial systems. And they looked around and they decided that the 6502 processor, which is what the BBC Micro used. Anybody remember the 6502 processor? Oh, good, okay, I am talking to the right audience. Good, 6502 processor, a lovely processor, a full 8 bits of data, and a very nice, simple instruction, flat memory model. Well, you don't really need anything other than a flat memory model when you've only got 8 data bits to work with. But it wasn't going to be powerful enough to actually run a business computer, which is what Acorn wanted to build next. So they looked around, and they found that there was a project being run at Berkeley in California. This was all about RISC, Reduced Instruction Set Computing. And this project had sort of looked around at the way that processors were being developed at that time. And some of the research they'd done is they looked at how Unix was running on a 68,000 processor. Who remembers 68,000 processor? Oh, good. Okay, excellent. Here's a piece of trivia for you. Why was the 68,000 processor called the 68,000? Anybody? No? Well, it's because that's how many transistors it had in it. So it was called the 68,000 because it had 68,000 transistors. But what they discovered was that only 30% of the instructions that the 68,000 processor could run were actually being used when you executed the Unix kernel. The Unix kernel was a fairly complex piece of software. So it was kind of logical to think, well, do we really need all of those instructions? Yes, there are certain times when they're being used, but a lot of the time it's actually a case of, well, you know, we could do without them. So what they decided to do was to build a processor which had more registers, less instructions, and that way they could get better performance because you had more registers, so the memory was closer to the processor, you didn't have to go out to caches and main memory and so on. And this is where Acorn kind of took that step, which is really interesting from the point of view of startups, because they looked around and they said, well, okay, you know, there's this RISC project, this looks really interesting, nobody's really building any processors around that, so let's just build our own. It can't be that hard, can it? You know, making your own processor, it's, other people do it, we can do it. So off they went, and they started building their own processors. And the first thing to come out of this was the Acorn RISC machine, and this was, in fact, the first sort of full version of that was the Archimedes device. Anybody here have an Archimedes? Oh, okay, somebody there, great. And that was a RISC-based architecture, 32-bit data, 26-bit, interesting number, address space, and 27 registers. And that's really where that came from. And so eventually they spun off the chip manufacturing business from that, from Acorn, and they became advanced RISC machines, which is where ARM comes from, advanced RISC machines, which I suppose really should be called ARISCM rather than ARM. Now, in terms of the ARM itself, where we've got to now, it is a 32-bit RISC architecture, and it's very popular, surprisingly so, really, if you think about it. ARM accounts for about 75% of all the embedded 32-bit CPUs that get shipped today. If you're using a mobile phone, chances are you've got an ARM-based processor in there. If you're using a tablet, chances are you've got an ARM-based processor in there. They actually sold 8 billion ARM-based processors last year, and current total is somewhere in the region of 35, 36 billion in total. 0 of those were manufactured directly by ARM. ARM themselves do not make the chips, they simply design them and then sell the intellectual property, the designs, to people like TA, to people like Freescale, NVIDIA, anybody who wants to license the technology and then actually build the chips themselves. And what they come up with is a set of things which is both an abstract architecture for the way the chip itself is designed, and then also a microprocessor core design and an instruction set. So you have these different versions of the ARM architecture, you have the different instruction sets. Raspberry Pi, as I say, uses an ARM 11 architecture, and it uses the ARM v6 instruction set. This is actually quite significant. ARM v7, as I'll mention in a moment, is the more modern one, and we'll talk about why that's significant when we get to Java. The really good thing about ARM processors is power consumption. Because if you want to build a small computer like this and you want to have it used by school children, if you want to build tablets, mobile phones, power consumption is your primary concern. And so ARM processors are very good at that. And in fact, with the Raspberry Pi, the way that it's powered, you use a USB, and okay, it needs 700 milliamps. Certainly if you're using the Model B and you're using the USB ports, then you need 700 milliamps, which is a bit more than most USB ports will supply. The standard for most USB ports or powered hubs is 500 milliamps, but you can get around that. So 5 volts, 700 milliamps. And I've got my Raspberry Pi running here. If I very gently put my finger on the chip in the middle, it's a little bit warm. I can feel some heat coming from it, but it's not hot. I mean, it's not burning or anything like that. You don't even need a heat sink on it. So, you know, that's the kind of thing which makes it significantly better for these types of things. You don't have to have a heat sink, you don't have to have a fan, all that kind of cooling stuff. So that's why it's very popular for mobile devices. From the point of view of the current ARM technology, ARM v6 is sort of the slightly older version of the instruction set. That gives you different types of processors that they make. There's the ARM 11, which is what the Raspberry Pi uses. There's also ARM Cortex-M, which is the mobile side of things that they develop. Some of those will use the ARM v6 architecture. ARM v7, which is the sort of current newest one, you have a range of different architectures around that. There's the Cortex-A for application processing, Cortex-M for mobile, Cortex-R for real-time. So there's different sort of structures to the processors depending on what your target is. They have announced the V8 architecture. That's not actually shipping yet, but should be fairly soon. That's going to be 64-bit data and addressing, 32-bit instructions with 30 registers. So that'll kind of take ARM to the next level. There are already companies that are building systems that can be used in data centers, so massive racks of ARM-based processors, because one of the things that's very important in data centers is how much power it takes to keep the things cool, how much power you have to put in to actually run the things. If you can make that power significantly less, you can make your data center run significantly more efficiently. So let's talk a little bit about Java on the ARM and the Raspberry Pi and some of the things that we need to think about there. So Java specifics for the ARM. Well, as I said, it uses the ARM v6 architecture. And one of the things with the ARM v6 is it doesn't, by default, support hard floating point. There's no floating point acceleration done on the processor, which means that if you're going to do anything other than integer arithmetic, you've got to do it all in software using a software library. As of ARM v7, hard floating point support, additional hardware in the architecture became standard, so you could rely on it being there. Having said that, the Raspberry Pi does actually have hard floating point processing capabilities built into it. So it's there, but it's not part of the standard. What you find from a performance point of view is that by not having hard floating point support and having to do it in software, that can really slow things down, especially in terms of the graphics side of things. And so what people have had to do in terms of supporting the Raspberry Pi in the best possible way is to actually compile the code so that it knows that there is a hard floating point accelerator on the chip and it can actually use it. So there's an ABI, an application binary interface, that you can take advantage of for that. So the Linux distros that you can download for the Raspberry Pi, I think it was about October last year, they released the Raspbian release, which is Debian, which they'd recompiled to use hard floating point support. And then Oracle had to do some work in terms of recompiling the JVM, again, to use the hard floating point support, and we released that just about at the end of last year. What we released was an early access version of JDK 8. And so I have to call it JDK 8 because we haven't defined Java SE and we haven't released Java SE yet. So it's JDK 8 early access. And this is an official release from Oracle, which has been tested on the Raspberry Pi. So we actually got a bunch of Raspberry Pis, we did the development work, and we tested it and made sure that it worked on that particular board with that architecture, with that chip, and so on. It uses the hard floating point capabilities, so the performance is better in terms of doing things like that. Also includes JavaFX libraries, so those are available on there. I was hoping to be able to show you some JavaFX running on the Raspberry Pis, but unfortunately, because we don't have HDMI or even DVI connectivity to the projector, I simply can't show you anything. I mean, I could turn, well, no, I can't even turn my laptop around because it won't work on there. So unfortunately, I can't show you that in the demos. So it has been tested for the Raspberry Pi. We're also working on Java SE 7. So there will be a Java SE 7 version for the Raspberry Pi that will come out later. Some of the things that we can do in terms of going beyond just the RISC processing and some of the things that we could take advantage of to help us improve the performance of Java further are some of the things that get included with ARM processors as well. So there are a number of extra bits that tend to get included. Because ARM processors are used a lot in mobile devices, they tend to have digital signal processing hardware built into them as well. That's, you know, for mobile phones, it's for handling voice calls and things like that. We don't really need that for the kinds of things we're doing, so there's not much we can take advantage of. Giselle is effectively bytecode execution in silicon, so that you can actually have a very simple virtual machine kind of thing which will execute bytecodes. So in theory, we could take advantage of that to try and get some performance improvements, but because it is fairly rudimentary in the way that it's implemented, there's probably not a huge amount that can be done there to really improve what we do with the hotspot virtual machine anyway. There are some other things that they've done to modify the instruction set in the ARM architecture. There's these things called thumb, thumb2, and thumb EE, which are all about basically shrinking down the size of the instructions that you need. So sometimes you actually leave out some of the operands that you're using because they can be inferred by default, and it reduces the density of the code that you're creating. That can be very useful if you're working in a very constrained embedded device where you've only got a very small amount of memory. So there's things like that you can do. Floating point, as I've already said, there's hard floating point support. There's also this thing called VFP, which is virtual floating point. So again, some things that can be done there. Neon is a set of instructions which are similar to the Intel SSE instructions. So they're designed for more media processing and doing things that require extensive work around codecs and things like that. And then there's also some security things that possibly we could use, which are trust zone, where you can actually have two virtual processors running on the same physical processor. So you've got one running in kernel mode, one running in user mode, and then you can protect between the two. And there's some hardware-based access control available as well. So let's talk about using Java on the Raspberry Pi and what we can actually do with it. So we know what it is now. What can we do with it? Well, the first thing that I sort of thought about was, well, okay, we've got sound output. What could we do in terms of making a sound? And it turns out it's actually harder than you think. One of the first things with the early distributions from the Raspberry Pi organization was that some of the sound drivers weren't sort of fully implemented. There was bits missing. That's now been resolved. So the necessary drivers that you require for sound are all included with the distro. Java Sound API is a bit hit and miss, I'd have to say, in terms of what actually works. One of the things is you have to make sure that you add the users, or add audio to the users group, so they have access to the audio device. Then you need to do modprobe snd underscore PCM underscore OSS, because that will create a /dev/DSP, digital signal processing device, which, if you're going to use the MIDI interface, will actually give you support for that. What I've found with using sound is that some bits work, some bits not so much. So WAV files will play if you get the right format. So if it's got the right bit rate and so on, then they will play quite happily. The MIDI, I had a lot of problems trying to get the MIDI interface to work, and the only success I've had so far has proved that it runs very, very, very slowly. So what I mean by very, very, very slowly is that, for example, I was testing it. I figured out this mod probe command that I needed. And I had my sample application. I ran it, sat there for a few seconds, nothing happened. I thought, oh, it's just locked up again like it did before. So I Control-C'd out of it. And then I thought, okay, I'll try something else, try running it again. And then I turned away because an email arrived or something, so I was checking that. And then about 45 seconds later, music started coming out of my Raspberry Pi. I'm like, wow, where did that come from? And it had taken that long to figure out how to get the sound working. So there's clearly some work we need to do there in terms of getting the sound working properly under Java. Similarly, free text-to-speech, which is an open source library that does Java text-to-speech. I've had some of that working. If you use the limited domain voice for telling the time, that works. But if you try and do the full text-to-speech, again, it seems to have some real issues. So that's one area that I do need to sit down and spend some more time working on. From a JavaFX point of view, as I said, we now have support for JavaFX in JDK 8 Early Access. What we really had to do there was to create a build that optimized what's called the Prism graphics engine so that we could get the best possible performance out of it. The Raspberry Pi, in addition to having the ARM processor, it's also got some pretty powerful GPU capabilities in there. So it's got a Video Core 4 GPU, which will actually do Blu-ray level video. So you can actually use this as a media player. And it's got enough power to be able to render Blu-ray quality graphics to your screen. And a lot of people have set these things up as media servers and connected them to their TVs and so on. And one of the nice things I found with my Raspberry Pi just a little while ago was that my Sony TV has a USB port on the back, and that will deliver enough power to actually drive the Raspberry Pi, so it's more than 500 milliamps. In terms of in terms of getting JavaFX running on the Raspberry Pi, what you have to do is you have to specify a command line argument, so -d javafx.platform. In the earlier builds of JavaFX, we supported X11. So you could have the desktop running on your Raspberry Pi, and then you could run JavaFX as an application on the desktop, and it would render onto the desktop. Because what we're doing with JavaFX is looking at embedded devices where it's very unlikely you're going to run an X11 desktop on an embedded device, we're not supporting X11 by default. There's a lot of discussion going on about, should we actually make it available anyway? But at the moment, the JDK 8 Early Access build doesn't support X11. So the only option that you can put on that command line is EGLFB, which will then render to the frame buffer. So that means you have to have the HDMI connected, and then you can actually see the application running through the frame buffer. That gives you a lot better performance, because performance on X11 is very, very slow. And not slow so much as it really thrashes the processor. So you see the processor running at 100%, even when it's not really doing very much. A couple of things that aren't supported in the early access version of JavaFX on the Raspberry Pi. One is media. That's something we are working on, so that may well make it into the final build. Web engine and web view, so that you can render HTML content as part of your JavaFX application. That's not supported either at the moment. I suspect that will be something we won't support for embedded JavaFX, just because, again, it's not something that will be targeted at with those types of applications. Serial port. So some of the pins on the Raspberry Pi allow you access to a UART. And the UART can be used to see things like the console messages. So what you can do is you can actually connect the pins on the Raspberry Pi, hook up a serial connector. If you have a machine that's old enough to actually have a serial port on it, then you can connect it directly, or you can get a USB converter from serial to USB. Thing is that serial tends to be at RS-232. And again, for those of you old enough to remember things like RS-232, RS-232 runs at 12 volts, and the voltage that you get from the UART on the Raspberry Pi is 3.3 volts because it's TTL. So you have to have a conversion between the two. There is a very nice chip that you can get, which is the MAX 3232 chip, And if you wire that up according to the diagram I've shown there with a few capacitors, you can very easily connect it to the serial port, and you can have RS-232 running from there. And what I do at home is I connect that to my PC so I can actually see the boot messages coming up, and then I can see what's actually happening as the device boots, so that I can also run my desktop and not have to keep switching between the HDMI output and my desktop. So one of the things that I did in terms of using that was I had a little board that I bought quite a while ago, which was an SP03 text-to-speech board. And that has a serial interface on it. So you can connect a device to that, and then you can send text to it, and it will actually talk to you. So I thought, okay, well, let's try and connect that to the Raspberry Pi. So that's what I've done for one of the demonstrations I'm going to show you later on. So in terms of making that run, the first thing you have to do is to stop the messages that are coming from the console going to the text-to-speech board, because otherwise it's going to take a long time as you listen to all the boot messages come up as your device boots. So what you do is you edit the etc initab file. Man, that really took me back in history too, because I used to work for AT&T doing Unix development. So it really took me back to remembering, oh yes, initab, that's where you start up things like the TTY and Getty. Anyone remember Getty? Okay, a few people, yeah, okay. And so you have to comment that out so that it doesn't create a login prompt on that port. And also you have to edit the /boot/command line.txt entry, so you take out any references to /dev/tty-ama0, which is the console port, and then you don't get the messages. In terms of the setting up the device itself, it's fairly simple. You set it up to 38,400 baud, 8 data bits, 2 stop bits, no parity, and then there's a very simple byte sequence that you can send in order to communicate with it and have it talk to you. From a USB peripheral point of view, USB is Universal Serial Bus, and in some cases, they're very much like serial devices. So some of the easy ones to connect will appear to be a serial device. So you have /dev/tty-USB0. Then you can just talk to it as if it were a serial device. You send bytes, you receive bytes. More complicated ones, you actually need to start digging into the USB code and figuring out how to communicate with them using some libraries. So again, there's some standard Linux libraries that are available. apt-get install libusb-1.0-0dev will give you most of the libraries that you need for that. From the point of view of communicating with that from Java, there is this very old API called JavaCom, which has been around for a very long time. And there's a nice package that's part of the distribution, so librxtx-java, which will give you an implementation of the JavaCom API that you can simply reference in your application. One of the things that I found is very useful is, by default, the librxtx package will only look for devices which are /dev/tty S something. And if your device isn't one of those, it won't report it as a serial device. You can get around that by putting in a system.setProperty gnu.io.rxtx serial ports, and then say /dev/tty-USB0 or /dev/tty-ama0 in the case of the console, and that will then enable you to pick up that port as a serial port, and then you can communicate with it as you would other ones. That's a handy little tip, that is. One of the things I bought a while ago was, this was on special offer at my local Maplin, and who's one of the electronics companies in the UK. And I saw that somebody had done something with this, and I thought, oh yeah, that'd be really good. So I bought one of these. It's got a USB interface, comes with a Windows-only driver, but the nice thing is that if you plug it into a Linux box, which is what our Raspberry Pi is, it will actually recognize it as a USB device, sets up a device that you can then talk to. What I had to do for that was basically write some JNI code, so write some native code that would actually talk directly to the USB libraries, and then wrap that so that I could then create a Java API that would enable me to control the robot arm from Java. It's a fairly simple protocol. There's 3 bytes that you send to it. The first byte controls the joints of the arm, second byte controls the direction of the base, and the third byte controls this little LED light on the end. I had to do a little bit of bit twiddling because you can't stop the motors individually. You have to stop them all at one time. So you can get around that by remembering which motors are moving, stopping them all, and then restarting the ones that you want to keep going. And that seemed to work quite well. So from a JNI code point of view, who's done JNI? Who likes JNI? Oh, it's one of the things that hopefully in JavaFX 9 we're going to rewrite, because it's not nice. And in fact, when I spoke to one of our engineers about this, he said, oh yes, we designed it that way. We want to discourage people from using it. And it was like, why? But anyway, so what you do is you write some native C functions that enable you to control the different parts of the ARM through the USB library, and then you just create native references within your code. Create native references within your code and have those work so that you can reference those from Java, and then you just call the appropriate method to make your robot arm move. So it's fairly nice, a little bit fiddly with reusing JNI, but you can work around that. From a Java coding point of view, it becomes very simple. You simply say, okay, I want to move this part of the arm, which direction you want it to move, and then you use sleep to create pauses so that it moves for a particular distance or a particular time. Another thing that I thought would be interesting to connect to the Raspberry Pi was a gamepad controller. So I went to Amazon and I bought one of those for a few pounds, and I thought, right, let's see what we can do with that. So the Linux supports most of these out of the box, so you don't have to worry about those. There's entries created in /dev/input that you can get to, and then there's a library called jinput, which allows you to work with things like gamepad controllers and other types of input devices. It is what I would describe as a mature technology, because it hasn't been touched since 2003. What I did was I moved that onto the Raspberry Pi, recompiled it, fixed a couple of glitches that I found. There was one thing where the build script didn't have a complete class path. There was a backwards compatibility issue that Linux had because they'd removed a particular hash define, so I had to kind of comment that out. And then for some bizarre reason, it would only work if I renamed the generated SO file, shared object, from libjinput-linux to libjinput-linux64. Don't know why that was, but it works, so I don't question it. And then the only other thing is that in order to access the input devices, you need to be you need rewrite access. So by default, it doesn't create them with rewrite access for everybody. So one of the things you can do on Linux is you can use UDEV rules. Who's used UDEV rules? Anybody? Who actually understands UDEV rules? Because I tried for ages. Just all I wanted to do was add read-write permission for a particular group of users. I could not make it work. So I gave up on that, and I used root. From a, well, it doesn't matter, does it? I'm not really sharing it with anybody. So I wrote some code that sat on top of jinput just to really give me a controller, which was based on my gamepad, so it just made life simpler. So I had button listeners, I had a joystick listener, and created a small library around that so that I could use that. And then I had a thing that ran in the background. So then you just add listener code, you say, okay, when a button is pressed, do this. When a joystick moves, do this. And I connected that to the robot arm. GPIO lines, these are the pins that you get on the Raspberry Pi. Various different things that you can access. So there's like obviously 5 volts, 3.3 volts. There's a ground connection. There's your UART, TX and RX lines. The green ones are the actual GPIO pins. So those are digital input and output. The purple ones are the SPI, I think, and the blue ones are the I2C, or it could be the other way around, I can never remember. So you've got a variety of different connections that you can make there. Now this is the earlier version of the Raspberry Pi. In the latest revision, which is the ones that most of you will have, they changed that slightly. Not by very much. Mostly they just exposed a bunch more ground pins, which is very helpful because you do need occasionally more than one ground pin. There's a second 5-volt line, and just one very minor change, which is the one that I highlighted there, where they changed the pin number for one of the GPIO pins. Again, no idea why they did that, but it doesn't make a huge difference. Using the GPIO pins is, well, it can be tricky, can be easy, depending on how you go about it. I started with the tricky approach, which was to basically start using magic incantations in native code and having to access the memory directly. Fortunately, somebody had already figured this out for me, so all I had to do was copy some of their code and then create some JNI code that sat on the top. So I won't go through the details of this, but it basically maps in some memory in your address space and then makes that available. Through some fairly nasty-looking bit twiddling, you can turn the pins on. You can set them to be either an input or an output. In the case of an output, you have to set it to be an input first and then tell it to be an output. And then you can set the pin to be high or pin to be low. And then, again, using JNI, you can simply write some wrappers around that and have some Java code which will say, okay, I want to use this particular pin, set this pin high, set this pin low. Py4j is the easy way of doing it. So somebody's actually gone and written a library to do this. And so what this will allow you to do is access the GPIO lines through a nice simple Java interface, pretty much in the same way that I guess I did it. They also have interfaces for I2C and SPI, although I haven't seen anybody who's actually written anything about actually using those yet. GPIO code is nice and simple, easy to use. One thing you do need is you still need root access. So in theory, I suppose you could change /dev/mem and give read-write access to everybody, but that might be considered a security flaw. So there are different things you can do there. It's still in development, so they're still working on that. It's version 0.0.4, some way from a 1.0 release. And in terms of examples of how you could use that, what I thought was, okay, let's see if I can connect a Lego motor. My 6-year-old son has lots of Lego, so I borrowed some of his. He didn't even notice. No children were harmed for this demo. And what you can do is you can get a very simple chip here. It's the L293D chip. And if you're going to buy one of these, I strongly recommend getting the D variant of this chip, because that has the necessary diodes that you need built into it. Otherwise, you have to put diodes on the outside. And literally, you just wire it up. So you connect GPIO lines to one side, you connect your motor to the other side with the power supply for the motor, and common ground. And it's as simple as saying, set this pin high, motor goes one way, set this pin low, and then set another pin high, motor goes the other way. Set both pins low, the motor stops. It really is quite simple to actually do that, so it doesn't require a lot of soldering or anything. A bit more about SPI and I2C. These are quite common interfaces for a lot of devices if you're looking at more complex devices. There's some experimental driver work. There's a guy called Chris Boot. That's a great name, Boot. Who has done some work on this, and so he built some kernel modules that you can use so that you get devices for SPI and I2C. Hopefully combining those with the Py4j libraries, it should make it fairly easy to do that. I haven't actually had a chance to try those yet. I've got a little display screen that I bought from China via eBay, and you can drive that through I2C, so I'm going to try and put that up and see if I can get that working, possibly with JavaFX next. So that kind of brings me to the end of the slides. So hopefully we'll show you some demos in a moment. So the Raspberry Pi is a very cool, very cheap computer. Great for teaching, great as an introduction to the ARM architecture. Java works pretty well, it's getting better. We have tested it, we've got support for it, and really the opportunities are pretty limitless in terms of what you can do. Certainly if you look on the web and you search for what people have done with Raspberry Pis, it's just amazing to see all the different things that are going on. Places for more information, java.oracle.com. There is a Raspberry Pi user guide that was written by the people who built it. It's more of a sort of introduction in terms of setting it up and using things. Doesn't really mention Java at the moment. RaspberryPi.org is the best place to go. There's forums there. There's lots of information about what people have done. And you can have a look at my blog where I've written up some of the demos that I've done here. Right, so I've got about 5 minutes, I think. Yes, I've got about 5 minutes. So let's see what we can do in the way of demos. Clear some space. Right. So what I have to do is I have to run the demos through SSH, because obviously I haven't got a monitor connected. Let me see, what are we going to do first? No, that's not the right one. Let's try. Good. because I've got two different Raspberry Pis that I'm going to use. Right. So, first demonstration is just a simple one. Right. What I'll do is I'll just start this, and hopefully, yeah. So what I've done is I've just set up a command line interface, so that when I use the joystick, press that. There we go. It will actually respond. So if I move the joysticks, you get the events coming up. Obviously, it would be nicer if it was a sort of graphical display, but since I can't run JavaFX, I can't show you a graphical display. Oh, yeah, it's a bit. Is there any way we could turn the lights down a bit in here? I'm showing my age by showing the green screen that I have. Okay. Yeah, it'd be better if we could turn the lights down at the front rather than at the back.
No, I don't even know how to.
Okay.
Sorry.
Okay. Right, okay. So anyway, so that shows you that we can actually get input from the joystick. I just terminate that. Now, if I turn the robot arm on, and just make sure that, yep, just make sure that I actually saw the robot arm, then hopefully, what should happen now, oh, yep, okay, that sounded good. Oop. There we go. So in theory, I could spend all day doing this. And I seem to have, oh, okay, yeah. We seem to have got into a situation where one of the motors has decided it's going to carry on going forever, so I'll just turn that off. It's good. That worked. Okay, so that was the gamepad. That was the robot arm running. So what I'm going to do now is... you think? Ah, yes. What I'm going to do now is I'm just going to unplug these, because one of the things you find with USB on the Raspberry Pi is that sometimes if you plug a different USB device in, if it actually requires a significant level of current to start up, actually, can we turn the lights back up again? Just a bit. Yeah, if you connect a USB device that requires a significant amount of current when it boots, it will actually reboot the Raspberry Pi. So while that's rebooting, I shall connect to. I thought I was going to connect to this one. Yeah. Good. So I'll connect to my other one. Now this one, I'm going to hopefully. Can we turn the volume down on the so the volume on the PC? I don't know how loud this is going to come out. We'll see. Because I don't want to deafen people when I do this.
Should be low now.
Okay, we'll try it first and then see what happens. Oh, poo. That's not what I was expecting to see. Hang on. No, I'm on the wrong. Okay, hang on. Should be on mine. Okay, I might need to. No, it's not. No, okay. Okay, I'm going to have to reboot that one. Actually, let me disconnect that. Okay, while that's rebooting, because the other one has rebooted, we'll go back to that. Oh, I know what. Idiot. You have to connect the network to be able to do a remote login. So the network's plugged into that one. I need to plug in the network into that one. Okay, I'll come back to that. Right, so what I've got here is something I bought a while ago, which is a Neuroski headset. And what it is it's an EEG monitor. So it has a couple of sensors on it, and they're supposed to work when they're dry, but if you make them a little bit wet, they do work better. So if I put this on my head, I have a habit of wearing strange things on my head when I do presentations. Now, what I'm going to show you now is I've got a USB dongle connected to my Raspberry Pi. And so if I remember to turn this on, this is going to be interesting because I'm trying to think of too many things at the same time. So right. So if I do, hopefully what it's going to do is, okay.
Request denied.
No, that's good. Okay. Great. Okay. So now what we're doing is we're reading my brainwaves. You're now seeing my mind in action. So there are two values that it gives you in addition to some raw data. It gives you two values. One is how much you're focusing your attention, and one is how relaxed you are. So, okay, let's just stop that for a second. Now, what I'm going to show you is briefly the idea of the Lego motor working. So let me just run the test for that. What that's going to do is it just moves the motor clockwise and anti-clockwise just to check that it works. So it was a sort of calibration thing just to see, okay, how long do you have to move it for a particular angle and so on. So that just does that twice, and then should finish. Okay, so now what we'll do is we'll combine the two. So we'll take my brainwaves, and I'm going to control the electric motor using my mind. Jedi mind training. Okay, so, okay. There we go. Right, so it's using the attention value to move the thing to a particular angle. So in theory, if I focus my attention on it, it should move. Well, it kind of moves, but I've got to say that it does seem somewhat random, which is probably a reflection on what's happening in my brain at the moment. I have a colleague of mine in the US, Angela, who actually she's a lot better at controlling the values that she gets from this, and she can actually get some real movement from this, or it doesn't look quite so random. Okay, so let me turn that off since that has actually worked. Right, let me reconnect. Change that network over to this one, so this might now, good, okay.
Yeah, of Ritter.
Of course.
How long time is
2 minutes.
2 minutes?
Please. Right. Maybe less. No. No. Okay. Right, I'll just try and run this very quickly. Let me just plug the audio in. Okay, might need to turn the volume up on that. Or not. No, it's not. I see nothing working. No. It's not. Okay, I think I'll have to abandon that one because I've run out of time. But hopefully this has given you some ideas about what you can do with the Raspberry Pi and some of the things you can connect to it. So thank you very much.